Hello everyone, today we will continue our discussion to the next part of the first chapter of basic mathematics, which is about set theory. So let's continue with defining the set. Well, the set is just a collection of well-defined objects, and these objects in a set are said to be elements or they're said to be members of a set, and mostly a set is represented by capital letters and lowercase letters are represents the elements of a set. And a set can be described in different ways. So set can be described or characterized by different ways. The first one is verbal method. The verbal method of describing a set, so which is using an ordinary English language and with minimum number of mathematical symbolizations, we can represent the given set. For instance, the set of mathematics graduate students, which is verbal expression of a set, and a set of positive numbers less than or equal to 5. The set of positive numbers less than or equal to 5. The set of vowel letters in English alphabet. The set of vowel letters in English alphabet. The collection of real numbers that satisfy the equation x squared minus 9, which is equal to 3, which is also another way of expressing a set using verbal method. The second one is complete listing method. If the number of elements in a set are able to be listed completely, or if we can able to if we are able to list all the elements in a curly brass without repeating and by separating the elements of the set by comma, then it's possible to list the elements, or it's said to be complete listing method, or it's said to be roster method. So the set of vowel letters in English alphabet, clearly the vowel letters in English alphabet are finite sets, so that we can completely list all the elements, so that A, E, I, O, U, R. So using that curly brass and by separating the elements by comma, we can represent the given finite set using complete listing method. The set of matter, the state of matter, the states of matter, so solid, liquid, gas, and plastic. So as a remark, the order of writing the elements in a set doesn't matter. And if we have an element A, B, and on the curly brass C, the elements of a set A are A, B, and an element. This one is also another element. But note that C and the C on curly brass are different elements. C and the curly brass C are different elements, are different objects, and C is an element of a set A, but the C is not an element in a set A. The set A is an element of it. Let B is an element of a set containing A within a curly brass, then the only element of B is an A in a curly brass, but A is not an element of B. A is not an element of B. The other one, the third way of describing a set is partial listing method, which is the number of elements in a set be too large to list them all, so that we look for a common property and then list some of the elements partial. So, for instance, set of all counting numbers, which is a set of natural numbers, which is 1, 2, 3, just then you would write 3 dots on the curly brass. The set of multiple of 7, the set of multiple of 7 is just you write 7, 14, 21, and then 3 dots, and you would continue just. So, which is infinite. So, mostly infinite sets are represented by partial listing method. It's represented by partial. The set of even positive integers, which is 2, 4, 6, ... Just this one are expressions of partial listing method of listing of set. The next one is set builder notation. So when all the elements of the set have the common property, if when they have the common property, we express the situation using an open proposition, P of x, so to describe set using. So A says that x says that P of x, or Ax dot P of x. We can represent these two. For instance, the following are examples to describe a set using set builder notation. So x says that x is a vowel in English alphabet, which is an expression. So we know x, which is a finite set, but we can represent this one using set builder notation. And the other one, B, the set B, T says that T is an even integer. Which is also representation using set builder notation. And D says that D is a set, says that y says that y squared minus y minus 6 is equal to 0, which is an expression of a set using set builder notation. Concepts in a set. The first concept is, the first definition is an empty set. A set which does not contain any element. The set which does not contain any element is said to be an empty set. Or we call it a void set or a null set. And it's denoted by this one or an open curly brace or a curly brace. And a set, for instance, a set X, an element of real number, says that x squared plus 1, which is equal to 0, is not is an empty set. So there is no real number that satisfies this equation, so that it's an empty set. And another one, the set x, an element of set of natural numbers, says that x squared minus 1, which is equal to 7, is an empty set, which is also there is no natural numbers that satisfies this equation, which is also another empty set. The other concepts in a set are finite and infinite set. A set containing a finite number of elements is said to be a finite set. If it does not have a finite set, which is an infinite set, So a set which consists of a finite number of elements is called a finite set. Otherwise, a set is called an infinite set. For instance, the set of two-digit positive integers, which is finite set, and the set of integers multiple of 5. The set of integers multiple of the number 5. Multiple of 5s are these ones are infinite sets, which is an infinite set. Another one, relationships between sets. So let A and B be two sets. Then if every element in a set A is an element also in a set B, or if every element in a set A is contained in a set B, then that A is said to be a subset of B, and it's denoted by this one. A is a subset of B, is denoted by. Mathematically, we can express in such a way. A is said to be a subset of B if for all x is an element of A, implies that x is also an element of B. So every x is an element in A. Every x in A is an element in B. If A is a subset of B, then B is called a superset of A, and it's denoted by this one. B is inverse subset. So from the definition, a set A is not a subset of set B if there exists at least one element in a set A that does not contain, that is not an element in a set B. So and for any set A, implicit set and set itself is a subset. And clearly natural number is a subset of integers, and integers is a subset of rational numbers, and rational numbers is a subset of real numbers. Given a set A containing 1 up to 6, a set B contains 1, 3, 5, and 7, and set C contains 2, 4, 6. Then clearly C is a subset of A. C is a subset of A, and B is not the subset of A. Because an element 7 is not found in set A. So that B is not a subset of A. A set A is called a proper subset of a set B if first A should be a subset of B, and B should be one element extra to A. A is different from B. A should be different from B. Written as A is a proper subset of A. So clearly A is a subset. So B is called a proper superset of set A. We can write B is a proper superset of a set. For example, X says that X is an even natural number. X says that X is an even natural number, and B set B is X says that X is a natural number. Clearly, even natural numbers are included on the set of natural numbers, so that set A is a proper subset of set B. Another one, if A is A, and then an element that contains B on the calculus, then A is a subset of A, and B, the calculus B, is also a subset of A. On the other hand, since B is not on the set A, B is not an element, so the set containing B is not the subset of A, and the element that contains AB is not the subset of A. AB is not the subset of A. The other nice definition is two sets are said to be equal. Two sets are said to be equal if they contain exactly the same elements regardless of the order listed or the possible repetition of the elements. Whatever they are repeated or regardless of the position of regardless of order listed, two sets are said to be equal if they contain exactly the same elements. If they contain exactly. Mathematically, we can write in such a way. A is a subset of B if for all x, x is an element of A, if and only if x is an element of A, which means that A is equal to B means that A is equal to B is if and only if A is a subset of B and B is a subset of A, vice versa. So for any set A, for example, for a set A 1, 1, 2, 3, 4, and set B 4, 3, 2, 1, 2, 3, 4, clearly 1, 2, 3, 4. Set A contains 1, 2, 3, 4, and set B contains 1, 2, 3, 4. So that set A and set B are equal sets because they contain the same number of elements. They contain the same number of elements. For instance, they show that these two sets are equal. Set S, x says that x is an even integer. X says that x is an even integer, and T, x says that x is the sum of two odd integers. The sum of two odd integers. So it shows that S and T are equal sets. So we want to show that S is a subset of T and T is a subset of S. We want to show two way of proving implies part and the bi-implies part, and forward and the backward one. So the forward is S is a subset of T, and the backward is T is a subset of S. So let's start. X is an element of S. X is an element of S. If X is an element of S, X can be written as 2m, where for m is an element of the integers. M is an element of integer. So if m is odd, now if this m is odd, then we can write m is equal to 2k plus 1. Then x can be written as m plus m, which is m is this one, 2k plus 1. So m plus m, 2k plus 1 plus 2k plus 1. We can write as the sum of two odd integers, the sum of two odd integers. Therefore, one way is satisfied. If m is even, when m is even, then m is equal to 2k. M is equal to 2k. M is even. Then x is equal to m plus m. Then m plus 1, we can write this one, m plus 1 plus m minus 1. So m is 2k. So which is 2m plus 1 plus 2m plus 1, when we are adding this one, 2m plus 1 plus 2 times minus 1 plus 1. So clearly 2m plus 1 is an odd, and 2 times minus 1 plus 1 is also another odd number. Therefore, clearly x is an element of T, either m is odd or even, x is an element of T, so which implies S is a subset of T. S is a subset of T. On the other way, the x is an element of T. We start from x is an element of T, then x, if x is an element of T, we can write as a sum of two odd integers, so which x is equal to 2m plus 1 plus 2n plus 1 for some m and n, an element of integers. So adding this one, we get 2m plus 2n plus 2, which is taking 2 as common with 2m plus m plus 1. So represent this one as k, 2k, it becomes 2k. So for k is equal to m plus 1 plus 1, which is an element of integer, which means that x is an even. X is, so which means that x is a subset of s. So Ts is, which is T is a subset of S. T is a subset of S. So S is a subset of T, and here T is a subset of S. So we can say that S is equal to T. S is equal to T. So two sets are said to be equivalent if they contain the same number of distinct elements. If they contain the same number of distinct elements, then we say that two sets are said to be equivalent, which means that they may not have the identical elements on the two sets, but the number of elements in those two sets should be the same. So for instance, set A, football, basketball, baseball, and soccer, and set B, painting, nickel, dime, and quarter. So you can see that 1, 2, 3, 4, 1, 2, 3, 4, even though they have different. So if they contain the same distinct elements, then we call the two sets are said to be equivalent. So we can say x is a counting number and bx is a positive integer. X is a positive integer is also another equivalent set. X is a counting number, this is a TS dimension, and x is a positive integer, also another. So A and B are also equivalent. So if two sets are equal, then they are equivalent. If two sets are equal, then we can say that they are equivalent. They are equivalent. Some important results in this set: a set itself and an empty set are always the subsets of every set. A set, an empty set and a set are always subsets of every set. And the total number of subsets of a set and proper subsets of a finite set are for the set containing n elements. If a set contains n elements, then the total number of subsets is obtained by to the power of n. The total number of subsets is obtained by to the power of n, and the total number of proper subsets is obtained by to the power of n minus 1, to the power of n minus 1. And the other result is if A is a subset of B and B is a subset of C, then we can clearly use that A is a subset of C. And the third one is if A is equal to B, if and only if A should be the subset of A and B should be the subset of A. A should be the subset of A and B should be the subset of A. The other good concept is a power set. Given a set A, the power set of A is denoted by P of A is a set whose elements are subsets of the set itself. So the sets whose elements are all subsets of set A are included under the power set. So all subsets of the set A are the power sets of set. The power sets of set. So the power set of A is B, says that B is the subset of A, is all the power elements of the power set. How to find the power set of a given set? So it's a procedure to find the power set of a given set. Assume that the set has n elements, the set having n elements is given. Then to find the power set of this set, first write the possible subsets having single elements, Then next, write all possible subsets having two elements, Then write all possible subsets having three elements. Then just repeat this procedure of writing all possible subsets of having n elements at a time as a given set is n elements. Then the fourth, form a set which, with the help of subsets obtained from step 1, step 2, and step 3, and adding the empty set, we can obtain the power set of the set. So this is the procedure how to find the power set of a given set. For example, given A is 1, 2, 3, then find the power set. The first step is all possible subsets of a given set having single elements, 1, 2, 3, 1, 2, 3. You'd write these single elements. On step 2, all possible subsets having two elements, 1 and 2, 2 and 3, 3 and 1, just like this one. All possible subsets having a set having three elements, which means the whole set A. The whole set having three elements, the whole set. And the last one is form a set with the help of the subsets obtained from the step 1 to 3, and adding this into set, we form a power set. So the power set of A is under the current class 1, 2, 3, 1, 2, 2, 3, 3, 1, and the set A and an set, which is the power set of a set A. And the note that if a set A has n elements, then the total number of elements in its power set is all the subsets, which is to the power of n. All the subsets, which is to the power of n. If A is an n-bit set, then the power set of A is just one element, which is an n-bit set, which is that n-bit set. And properties of a power set: if A is a subset of B, then the power set of A is a subset of the power set of B. The power set of A intersection the power set of B is equal to the power set of A intersection B. The power set of A intersection the power set of B is equal to the power set of A intersection B. But that the power set of A union B is not equal to the power set of A union the power set of B. The other one is universal set. Universal set is a set used that includes all elements under consideration in particular discussion. In particular, set of Latin letters, set of natural numbers, a set of real numbers, the set of points in a line, and just like that one. The other good concept is set operations. Let A and B be n into sets, then the union of A and B is the set of all elements in a set A or in a set B. So is a set of all those elements which belongs to A, either A or in B, or in both elements. So the symbol this one represents denotes the union of two sets. And mathematically, we can express in such a way: A union B is equal to x, that x is an element of A, or x is an element of B. X is an element of B. So the union of two sets is mathematically represented in such a way. So the union of sets A and B is represented using Venn diagram in such a way. The union of A and B is whole sets in this set and the whole sets in this set. Is the union of the sets. Some properties of unions of set. Union is commutative. A union B is equal to B union A. Union is also associative. Union B set is A, identity law, and A union A is also itself, and universal set union A is a universal set, which is a law of universal set. The other one is intersection of two sets. Given two sets A and B, the intersection of A and B is a set of all elements which belongs to both A and B. Those elements in A and B should exist in set A and set B. Those are said to be elements in the intersection of. So it's denoted by A intersection B. Read as A intersection B. This supports the intersection, and mathematically we can express in such a way: A and B, A intersection B is equal to x, is that x is an element of A, and it is and x is an element of. You can see, remember that if the union of A union B is expressed, x is that x is an element of A, or it says or x is an element of B, either of the two. So the intersection of the intersection set of two sets, the intersection of two sets is the element which belongs in both sets. The element which found in the two sets is an intersection of the sets. And the intersection of a set can be described this one. So the intersection of this A and B is this part. This part is the intersection part, which is this part. This part is the intersection part of the intersection of the two sets. For instance, let A be the set of even positive integers. The set of even positive integers, and B is the set of prime positive integers. Prime positive integers and the set of even integers. So the intersection of A and B is only 2. 2 is a prime number and also it's an even number. And two sets are said to be disjoint. Two sets are said to be disjoint if their intersection is an empty set. If the intersection of two sets is empty, then we call it the two sets are disjoint. Given two sets, A is 0, 1, 3, 5, 6 and B is 1, 2, 3, 4, 6, 7, then A union B is clearly those elements which are found in A or in B is included on the union set. So 0, 1, 2, 3, 4, 5, 6, 7 is the union, and the intersection of the two sets is 1 is an element on both sides, and 3 is also an element on both sides, and 6 is an element on the two sets. So the element which is found commonly in the two sets is registered under the intersection set and the intersection of the two sets. So another one, the set of positive even integers. The set of positive even integers. The set of positive multiple of 3. The set of positive multiple. So what's the union of an intersection of the sets? So clearly the set of positive even integers 2, 4, 6, 8, 10, 12, 13, like this one. The set of positive multiple of 3 is 3, 6, 9, 12, 15, 18, 21, and 30. So A union B is such that x is a positive integer that is either even or a multiple of 3. That's either even or a multiple of 3, which is 2, 3, 4, 6, 8, 9, 10, 12, 14, 15, 16, just like that one. And the intersection of the two sets, is those even positive integers which are multiple of 3. The intersection of A and B is those even integers which are multiple of 3 should be included on the intersection of the sets. So 2 is not a multiple of 3, 6 is a multiple of 3, clearly you will take that one. 12 is a multiple of 3, which is you will take that one. 18 is a multiple of 3, which you will take that one. 24 is a multiple of 3, which is if those events which are multiple of 3 are included on the intersection. Therefore, 6, 12, 18, 24, which is just, we can express another set using set builder notation. X says that x is a positive multiple of 6. Those elements are positive multiple of 6. So we can complete the intersection and the union of two sets in such a way. Some properties of intersection of sets. Clearly, intersection of two sets is commutative and also it's associative. And implicit intersection A is an implicit set, and A intersection universal set is A. and A intersection A is itself. If A, B, and C are any sets, three sets, A intersection B union C, which is a distributive property of intersection over union. A intersection B union C is A intersection B union A intersection C. Similarly, you have given three sets, A union B intersection C is A union B intersection A, which is the distributive property of union over the distributive property of union over intersection, which is this one. The other one is a complement of a set. There are two complements, relative complement and the absolute complement. The relative complement is when we are comparing two relative sets, the relative of the relation between two sets. And the absolute complement is a complement with respect to the universal set. The complement of a set with respect to the universal set is said to be an absolute complement. So the difference between two sets A and B denoted by A minus B, which is just like this one, is a set of all elements in A which are not in B. All elements in A which are not in B. A without B, or A the relative complement to B. So A without B, or the difference of A to B, is X an element of A, and X should be not element in a set A, in a set B, in a set B. And we can graphically see this one. Those elements which are this part are said to be A with A relative to B, A relative, the difference of A relative to B, so which is that part. And if the absolute complement is, let given AB is a subset of the universal set, then the absolute complement of A is just those elements. We can represent this one, A the power, this one, or A the power of C, just like this one, is defined as those elements which are not in A, set A. Those elements which are not in a set A, but they are in the set of the universal set. So clearly you can see this part. A is this one, so those elements out of A are complement of A, are the absolute complement of A. So those parts, the black one is the complement of set. So A intersection A complement is always in bit set. A intersection A complement is an in bit set, and A union A complement gives the universal set. A union A complement gives the universal set. Properties of a complement: for any two sets A and B in the universal set, A complement is A itself, double complement. A union A complement is universal set, and A intersection A complement is a bit set. A intersection A complement is a bit set. The complement of an implicit set is universal set, and the complement of the universal set is an implicit set. And A union B complement is A complement intersection B complement. And A intersection B complement is A complement union B complement. The complement changes the sign of the intersection in the union, and changes the sign of the intersection. So A union B complement, union will be changed to intersection, and complement of the sets also. The complement of the sets and also the sign of the intersection and the union will be also changed. So if A is a subset of B, if and only if the B complement is also a subset of A. Have you seen this one? If E is a subset of B, then the B complement is the subset of A. A without B, or A, the difference of A with respect to B is equal to A intersection B complement. A intersection B complement. So these are some properties of a complement. The other one is symmetric difference. So the symmetric difference of two sets A and B is denoted by this one. The symmetric difference of two sets is denoted by this one. Is a set defined by this one. A without B union B without A. Those elements which are not found in set, have you seen? Only in set A, and those elements union those elements which are not found in set B, in set A. Or we can write in such a way: A union B without the intersection. Have you seen? A union B without this intersection is a symmetric difference of the two sets. The symmetric difference of the two sets. So we can define symmetric in either of the two. The A without B union B without A, or A union B without A intersection B is the symmetric difference of the two sets. Find the symmetric difference of A to B. A is 1, 3, 4, B is 2, 5, 9, 11, and A is 1, 3, 6, 1, 11/12 and b is 1/6. So we have here, we have the solution. So a is this one, b is this one, then a without b is a without b. A without b here, a without b, 1, 3, 4, the whole set A, and b without a is the whole set B. So A symmetric to B is A without B union B without A, which is the union of the two sets. The union of the two sets. And we have A is here 1, 3, 6. This one B is here 1, 6. So A without B is A without B. A without B is 1, 11, 12. 1. A without B is 1, 11, 12. And B without A. B without A is B without A is a repeat set. B without A is a repeat set. B without A is a repeat set. You can see it clearly. Then the symmetric difference of A and B is A without B union B without A. So which is 3, 11, 12. So which is 3, 11, 12. The other one is the basic counting rules. The A union B is equal to B is obtained by the number of A union B is obtained by the number of A plus the number of B minus the intersection of the two sets. If the two sets have an intersection. And if we have three sets, the number of A union B union C is obtained by the number of A plus the number of B plus the number of C plus the minus the number of A intersection B minus A intersection C minus B intersection C and the intersection of the whole sets. And the number of the complement, the number of the A complement intersection B complement, which is also called the number of the union complement, the A union B complement, is obtained by the universal set minus the number of A union B. Most of the time, this question may be asked. So sometimes find the number of elements which are found in A, either in A or in B. So when we are saying like that one, you will use this one, neither in A nor in B. When the question asks those elements which are not found neither in A nor in B, if it's asked in such a way, we will use this one. After completing this one, we find this one. So sometimes A union B, we can find A union B in such a way. The number of A union B is obtained, number of A without B plus number of B without A plus number of the intersection of the two elements. The number of A union B is either, you can use this one, or sometimes you may use this one. For example, in a class of 60 students, 25 students play cricket, 20 students play tennis, and 10 students play both games. Then find the number of students who play neither games. Have you seen? Find the number of students who play neither games. It's not either or, it is neither nor. It's not either or, but it's neither. So first let's find either or. Those play cricket or neither cricket nor tennis, then we will find neither. So let's see the cricket students who play cricket and T denotes the students who play tennis. So the number of students who play cricket is 25, and the number of students who play tennis are 20. The number of students who play both of them are 10, and the universal set is in a class of 60 students, which is 60. So we know that formula, number of elements who are found in the union is the number of elements in C plus number of elements in T minus the number of elements in the intersection. So 25 plus 20 plus minus 10 is 35. Now it's not our target, but our target is to find those elements which are found in C and B. So a number of A union B complements in the universal set minus number of those elements in the universal set. So 60 minus 35, which is 25, which is the students play is 25 students play neither the games. The other one, each student in a class of 40 students study at least one of the subjects: English, mathematics, geography. 60 students study English, 22 students geography, and 26 students mathematics, and 5 study English and geography. 40 students study mathematics and geography, and two English and geography. Geography and two English and geography and mathematics. Find the number of students who study English and mathematics. So let A, G, and M denote the set of students who study English, geography and mathematics, respectively. So it's given the total number of students is 40. The number of students is 40. The number of students who study English is 60. The number of students who learn geography is 22. The number of students who learn mathematics is 26. Also, the number of students who learn both English and geography is 5. The number of students who learn maths and geography 40. The number of students who learn all the subjects is 2. Our target we want to find is the number of students who learn maths and English. The number of students is who learn, it's not given. Find the number of students who learn English and mathematics. So it's not given. Then using the definition of finding the number of elements for the set of the set of three sets, for find the number of elements who are found in the three set is, and the union of the three set is obtained by the number of elements in English, the number of elements who study geography, number of elements who study mathematics, minus the number of students who study English and geography, minus the number of students who study English and mathematics, minus the number of students who study mathematics and geography, minus the number of students who study English and mathematics and geography. So by calculating those things, you will obtain that the number of students who study mathematics and geography as 7. So this is the end. Thank you for watching this video. Please follow me by subscribing my YouTube channel. So if you have any comment, please write on the comment section. I will improve the way I will forward those materials. Thank you for watching.